Start? I don't think there's anybody outside. Okay, welcome to the third day, and the theme today is cosmology. The first speaker this morning is Ilya from CETA, who will tell us about cosmological radiative transfer code comparison project.
Hello. There are a number of people in the app.
Turn on. Yeah, there's a button. Oh, that's okay. It's on here.
Can it be more on?
Yeah.
Okay.
Very sensitive.
It seems there are two levels of on. Okay. So I'll be talking about a fairly technical project. Is it too loud? Is it too loud? Okay. So we have been working on this for already a couple of years, a large number of people, and many of them are here today. And there is a website which I'll mention again later, where we publish all the data, results, papers, workshop information, and everything else. Okay, so there were two papers result of it. The first one is already out, and since there are too many people to list, I just made a copy of the first page. So all these people have been sending me data, and we have been discussing things and helping me with analyzing the data. So obviously I need to mention everybody's name, or at least show it. So the first part of the project was on static density fields, so not entirely, at least not obviously relevant here, but as we'll see, this is important to figure out first because it's simpler type of problems, and it will be nice to first figure out the simple things before going to more complicated ones. And in this part there were 11 codes participating, and new ones are also joining now. And these codes included all sorts of different methods, from ray tracing with both long and short characteristics, Monte Carlo moment methods on various types of grids, or even without grids, based on SPH particles. And so they cover most of the spectrum of possible approaches to radiative transfer. And I'll talk about the tests in a moment. Then the second one, which as you can see from here is still preprint, but I'm working on it, and hopefully it will be done within the next few months. So again, a large number of people, some of them the same, some of them new. The reason why not everybody is participating in the second part is because not all codes actually are coupled to hydrodynamics still. But then there are new ones joining all the time, so again, large number of people. In this case, there are 8 codes, and again, variety of ray tracing, possibly Monte Carlo. It's not clear if it will join, but anyway. Moment methods, particles, SPH particles. Then in terms of hydrodynamics, there are again all the spectrum of methods, so Illyrian, Lagrangian, SPH, which is actually a kind of Lagrangian. Adaptive mesh refinement, Riemann solver. Many of those codes are also parallelized, so they can do fairly large problems and complicated ones, but the tests are relatively simple ones, as you'll see. Okay, so what is the aim here? As you quite well know, the full radiative transfer problem is quite expensive and practically impossible to do in perfect precision. So you have to employ various approximations. There are many dimensions, obviously, both in space and in frequency, and you have to do certain approximation to make it possible to handle. And the idea of this project is to validate the codes and evaluate their reliability, limitations, to see what they can do, how reliable the results are, and can we really believe them. And the problem is that very few very simplified problems exist that have an analytical solution, which ideally, this is the perfect test because if you know the answer, obviously you can reproduce it or not reproduce it, and then you know if your code is working. But there are basically no such problems, or very few. And the next best approach, which we are employing here, is to just collect various different codes which are completely independent, different methods, and see if they reproduce the same results. And if they do, there is a good chance that the results are actually correct. How we have picked the problems, we tried to get problems which are simple enough and clean enough to actually have some understanding even beforehand what the result will be. And also there are not too many variables to actually control and make sure that and then we pick them with increasing difficulty, so there are also some interesting problems, not too simplified ones, so we can actually test the full range of the code abilities. And we also try to make them astrophysically interesting, even though simplified. Everybody is welcome to join. This has always been the principle, and of course from this audience, if anybody is interested in doing the problems, you can do that and send me the results. We have been already doing a couple of workshops. There will be another mini meeting today after the day. And results are, as I said, published in series of papers on this website. And on the website I'm putting all the data on, so you can actually compare directly to the data, not just to figures from the previous papers. So what is specific for cosmological radiative transfer? We have already seen quite a bit of radiative transfer last couple of days, but in cosmology it's actually a fairly different case, and it's both simpler and more complicated at the same time, depending what you want to do and depending how you look at it. So the main problem we are trying to solve first we are interested in is ionization of the universe, the feedback from the first stars and so on, which is the most interesting radiative transfer related cosmological problem. And in this case there are very large scales involved, from kiloparsecs to hundreds of megaparsecs. Again, different problems require different scales, but they generally are much larger than what we have been talking up to now. And they involve many sources very often, up to hundreds of thousands, maybe even millions at some point in the future. And in this case, low densities are involved, the IgM type densities, so much lower than the interstellar medium and surely much lower than even a star. So ionization fronts are typically fast. They propagate much faster than the hydrodynamic response of the gas. So they are so-called R-type. But when they hit a denser region, for example, or inside the halos, they convert to D-type, which is preceded by a shock front, and then in this case the hydrodynamics becomes important again. So you could have both, and usually you have both, depending on the scale you're interested in. And then usually you have to do it in 3D, and the density fields are highly homogeneous, some places much denser than others, and they are quite complicated. And very high optical depths are always involved, both inside halos, but also when you have relatively coarse cells, even the intergalactic medium, which is such a rarefied medium, once you take a cell which is, for example, half a megaparsec, you can calculate the intergalactic medium optical depth. It's very high, even though the density is low. So you have to be able to handle high optical depths. And typically we are interested in mostly primordial chemistry because metals, at least early on, are still not very important, but later they become important. So in principle we have to also include metals later on. And the chemistry is generally non-equilibrium, which is again a different case. Very often in other problems you can do with equilibrium chemistry, but here generally not. What are the tests? First we wanted to test, before even starting, wanted to test the basic physics, so the rates we have used, and then the single zone evolution, just ionizing up and then ionizing down, cooling down. And we tested what, for example, the effect of different rates we have used on the propagation of the ionization fronts, because this is obviously important and it can actually change the results, as I'll show in a moment. The first test is the simplest possible case. So the first 4 tests were from the first paper, pure radiative transfer, density field is fixed, and you're just propagating ionization fronts. So the simplest possible case, and of course somewhat idealized. So the first one is pure hydrogen isothermal H2 region expansion with even monochromatic light. So everything is maximally simplified, the most classic and the simplest possible test, until it reaches the Strange sphere. Then the second one is the same thing, but includes temperature and can actually follow the temperature state of the gas as well. But otherwise, everything else is the same, and the spectrum is already evolved as well, not just monochromatic. The third problem is you have a dense clump, plane parallel ionization front, which gets trapped in the dense clump and forms a shadow. And the fourth test is multiple sources. In our case, we actually did 6, but that's not really important, in a fixed cosmological density field. So again, no dynamics, but otherwise sort of made to look like a real simulation. So we have real cosmological density field sources which are assigned to certain halos which are found on that field, and then we follow the evolution as it ionizes up. The current tests from the second paper I'm working on, and this is work in progress, so you'll see relatively fewer results. The first one is again the classical H2 region expansion, but this time with gas dynamics. So in this case what you have is you start with R-type front very fast, then once the recombination starts to compensate for the incoming photons, then you convert the I front slows down and converts to D-type, which starts getting pushed by the pressure out, and then you get a shock front and D-type front expanding further, much further. And this is the R to D-type transition is what we're most interested in here. The second test is again H2 region expansion, but we have a source in the middle of 1 over R density R squared density profile. So something similar to a small galaxy. So the source is in the middle, a core, little core in the middle, flat core, and then 1 over R density profile. So it looks like something like inside-out dwarf galaxy photoevaporation. And the last problem is just the photoevaporation of a dense clump from the outside. So it is more interstellar type problem. In cosmology, of course, usually clumps are small galaxies, so they have some density gradient, but we wanted to make it simpler and not complicate things too much. So first, the rates that we have been using. I'm not expecting you to see all the line types, and that's not really important. I'll say what I want to point out. So basically, all the different codes send me their rates, and they were plotted here. So they are recombination rates, case A, case B. Then there are collision ionization rates, cross-section for photoionization, then recombination cooling, case A, case B, then the ionization, collision ionization cooling and line cooling, and the free cooling. So all this, as you see, there are significant differences in the rates, and especially at very high temperatures. On the other hand, in our type of problems, unless you get very strong shocks, which in this case we are not getting for these problems, usually you are in the regime around 10 to the 4 temperature, not 10 to the 6 or 10 to the 8. So in this case, these differences are actually somewhat smaller than they look here, but still there are some significant differences in the cooling. And other rates are much more precise, or at least the various sources agree what the rates are. So there is significant uncertainty here. So how does this uncertainty...
How many reactions roughly do you have? I mean, you didn't get to show any background here, I think.
Yes, well, there are not many reactions. Basically, these are the ones that I showed. The other way. So we have recombinations, obviously, collision ionization, photoionization, and that's pretty much it. With pure hydrogen, that's what you can do. We don't have molecules here, to just make it simple, and we don't have helium, so there is basically these are the reactions and the corresponding cooling rates.
Hey, Ilion. Generally, when we do primordial chemistry, they're on the order of 30 reactions in general, when you include hydrogen, helium.
Yes, once you include hydrogen, helium molecules, there are many more than 30 reactions. 30 are the sort of more important ones.
But here you're doing 3, is that right?
Here we are doing, yes, basically.
And they're of course nonlinear equations, so, and you know all the coefficients, so how can there ever be a difference between different codes?
Well,
you just undercut 2 years of the poor guy's work. I mean, you know.
No, I mean, I just want to understand. I mean, he's solving a set of nonlinear equations, isn't that right?
well,
And then there's differences.
you have to, okay. Solving the chemistry is relatively easy. I mean, actually, with pure hydrogen, it has an analytical solution, you know it.
Mm-hmm.
So the chemistry isn't the problem. There are several other things which I'll point out to. So the first uncertainty is that we don't really know the rates, which I'm saying here.
Mm-hmm.
And so they are sort of known, but as you see, this is sort of big range. So rates are known in some cases within factor of 2 or worse.
But if you do the benchmark, are you not agreeing on the input parameters, or what do you mean?
Well, everybody's using their own rates because this is how they do real problems. So we were thinking first, should we unify the rates and just use the same one, so we test only the radiative transfer.
Yes.
But this is not how you use your code. You use your own rates and you think they are better than the others for one reason or another.
Perhaps it's as well at this point to state that this cosmological application inherits codes that were originally designed for other applications, such as interstellar matter, stellar atmospheres, and things like that. Now, they have been sort of tuned and optimized to reproduce the observations there as well as they could, with the rates that Ilion is quoting, right? And unless they have a specific reason for going back
Actually,
to that,
very often
they
we
use the
are
same
changing the rates because, for example, things like, very often it's assumed things like coronal equilibrium, which is here is completely wrong. I mean, just, you can't use it. Totally off. So there are all sorts of things which you need to fix. Some people also, play with the rates and just make sure once something newer and better comes out, they change it and see what the effect is and all that. So all this, this is just the first uncertainty that we are talking about. Then how you are solving the radiative transfer is another thing, because just solving the chemistry is not quite enough. Once you have a very optically thick situation and dynamics, things get rather more complicated, as we'll see. So what is the uncertainty based on the rates? Just to estimate it, we put all the different, basically there were a couple of groups of rates, and we put them in the same radiative transfer method. It's not important at this point which method, but just the same method, so the radiative transfer isn't different. We just wanted to see the effect of varying rates. And as you can see here, you can get, for example, in the position of the eye front, this is just uniform medium expansion of eye front. You can get easily something like 10% difference in the position. And then maybe in the velocity you can get also a factor of 2 difference when it slows down. And this is the structure inside, the ionization structure and the temperature structure, and again you can get up to 40% off in ionization and 20% off in temperature. So this is just the effect of rays.
The statistics no way, I mean 3 curves agree and 1 disagree. So
that's because the 3 curves that agree were using more or less the same sources for rates. That's why we don't have 11 curves, because some of them were using literally the same sources and others were using a little bit different sources. So this is just showing the range here, not so much doing statistics. Because there are not that many sources. For example, if you look carefully for a combination, say, let's just take one example. There are basically 2 sources in the literature, and then they are propagating within the literature, and You can believe one or the other, but that's it pretty much. Nobody has calculated. There are not 20 different sources for recombination rates. And then everything else is the same thing. Cross-sections, collision ionization, anything else that you can think of. So in terms of the rates we have been using, this is the variation you can get from the different sets of rates. So this is some uncertainty that we have to keep in mind. And it's basically not part of the radiative transfer per se, but obviously results depend on it, so we have to, well, I hope rates are calculated better at some point. I'm not personally doing this, but it's obviously important. Okay, so the first and simplest possible example, in which case we actually know the analytical solution, and it's shown here with the thick black line, which is uniform density, source in the middle, and then it just expands until it reaches the Stromian sphere when the recombinations bounce ionizations. So a very simple problem. And the different codes are shown here. Again, I'm not expecting you to see which we switch, but that's not the point. And the variations in radius, for example, are shown here. So within few percent, basically, they do agree. And there are some outlying ones, but even the worst case, it's something like 5% or so. So their results are fairly reliable in this sense. And they agree over the whole range. This is time evolution versus, so for something like 4 recombination times, so until you actually reach the Stromian sphere and final equilibrium. And the velocity as well agrees quite well and follows the actual curve.
Julian?
Yes.
The area that you're showing must be a function of the resolution in time and space. So
I think here it's
everyone
mostly...
agreed on a resolution to...
Yes, we fixed the resolution the same for everybody, but the time resolution is not fixed. So time resolution was left to people to decide what they need to do this problem. Actually, some of these differences, most of these differences, I think, is due to recombination rates. The different recombination rates, especially towards the end, because at the end there is nothing else. I mean, you are in equilibrium. There is source in the middle, recombinations, and then you attenuate the flux until you run out of photons. So any difference in the final size is actually due to mostly to recombination rate. And the actual structure is also a little bit different. So it's shown here. This is the final Stromian sphere for all 9 codes that did this problem. So one thing to notice here is that first of all, the eye front isn't sharp. So here what is shown with this little air bar is theoretically you can calculate what is the intrinsic thickness of the eye front, which is based on the mean free path of the photons. And the photons, even though they are monochromatic and very simple problem here, still the eye front isn't sharp. It never is sharp. There is some intrinsic thickness just because of this mean free path. And the mean free path is not quite trivial. I mean, you can see it here. So this is the thickness from 10 to 90% ionization of the eye front. Or in this case, actually, it's not the front anymore because you reach the final equilibrium. Another thing to notice here is that some methods are, for example, a bit more diffusive than others, particularly moment methods in this case. So they make a little bit thicker boundary than that even. And the last thing is that in some cases you get some anisotropies, which is also somewhat unphysical, and it depends on the resolution in this case, presumably. So, for example, this is Monte Carlo method. So if you send enough rays, you can make it smoother than that, but it just depends how many rays you send out, so you can get it relatively more anisotropic. And also it's thicker than the others, as you can see.
So how do you make the choice then? I mean, the dot looks now very much different, but until you could make it different again, I mean, now that the figure's different.
How do...
the codes could make it different, so what is the point then of this comparison? Do you say, oh, you get the same computation time, or what is the same for the codes?
Well, what is the same is the resolution.
Spatial.
Spatial resolution is the same. And the basic problem that we are solving is, of course, exactly the same. Otherwise, we left it, we are not trying to compare computation time because this is a little bit tricky as we explained it in the paper. I don't have too much time to explain it, but it's difficult to compare computation time. It's much more involved problem, and in this case it's also a very small problem, so it actually runs very fast for any code pretty much, so that's not really the main thing is can we get the same answer based on some reasonable amount of computation essentially, and we left it to people to decide what computation you're doing, how long you're running it for, what time step you're picking. But we wanted just to compare, is the answer reliable? And the answer in this case is reliable because although I'm pointing to some small differences, the bottom line is that the Sturmian sphere is exactly the same. I mean, there are no differences within few percent as I showed just in a moment.
So I think the goal was to allow people to use the code in the same way that it would be used in the cosmological case. So if decisions were made about how accurate it needed to be, that was the level that was supposed to be adopted for the comparison. Now that varied from code to code.
Actually, strictly speaking, even controlling the resolution isn't the most straightforward thing. Because, for example, there is an SPH code here. So if you have 128 cube spatial resolution, what is the corresponding spatial resolution for SPH? Or, for example, the unstructured grid that Vincent was talking about the other day. Again, what is the corresponding resolution is a little bit fuzzy. At the end, we are interpolating on the same grid, but how it is done in practice is basically, the idea here was, can you get the answer and you don't know the answer beforehand, so you are sending the results and you're comparing with the others, and they become, and you can show that this is reliable in this case.
Yeah, the simplex case there, I think a lot of those features are really due to the interpolation and the mapping correct.
Yes.
It's not the code.
I'm not saying it is the code, I'm just saying that it's left to the people and it's difficult to say what exactly is the corresponding resolution. Because, I don't know what is the corresponding resolution. They surely didn't take 128 cube cells, because it wouldn't be the same thing. So, but anyway, the point is, you're getting always the same size and the evolution is the same, which means that within a few percent you can do this problem. And it's reliable, it doesn't depend on which method you are using.
What we see is temperature, yeah? Or what?
No, this is just ionization fraction. There is no temperature. In this case, temperature is fixed.
You're only at test 1. And you've got about 10.
Actually, you have about 7 minutes.
Yes, I know. Well, people are asking questions. I mean, this is the discussion, right? What can I say? So you can also compare the internal ionization structure, for example, and again, there are some details that are different, but the position and basics of the internal structure are the same. The mean ionization fraction, histograms of the various quantities, again, they agree quite well. So you can see here the thickness of the ionization front, for example, is slightly different, but otherwise results are. So this is the same, but with temperature. And in this case, of course, there is no analytical solution because temperature varies, so you don't really know the answer. But again, results are agreeing within something like plus minus 5%. And the main differences that come around actually are coming from the temperature, as I'll show you. So again, the size of the ionization front, this is the initial fast expansion. Again, they are all agreeing the same place. But in terms of temperature, there are significant differences, and there are many reasons for this which are described in the paper. For example, this code has equilibrium chemistry and assumes sharp eye front, so it cannot get this hardening of the spectrum, and so on. So The main differences here are how you handle the temperature and how you handle the photon hardening. So the spectrum, the hard photons have lower cross-section, they run much further, which means that you get this much thicker eye front. And there are significant differences in how thick the eye front is depending on which method you are using. And this is also influencing how fast it's moving, the ionization front. And again, the ionization front is relatively unsensitive to it in this case, but still there are some small differences. But there are big differences in the temperature. This is the final stratosphere. And again, the structure is somewhat different. The thickness of the eye front is different. But it mostly concerns the hard photons that are beyond the ionization front, not so much the position of the ionization front in this case. The internal structure, I already showed this, the temperature. So the main differences, as I said before, are due to the temperature. So this lowest one here, actually we found later that it was run with incorrect parameters, so don't pay attention to this. But all the other ones do differ within something like factor of maybe 50% or so in temperature. And the hardening of the eye front is here. So any preheating here is due to the hard photons that are actually ahead of the eye front penetrating much deeper. And again, there are some significant differences there. And this will show up in the dynamics if I get to it. Okay, the eye front trapping in a dense clump. This is how it looks at the initial phase. So it hits the first, you have R-type eye front which just goes through the box very quickly. Then it hits the clump and forms a shadow behind it. This is the ionization fraction. And the shadows are generally quite agreeing with each other. The only difference is this one, but this is SPH, so it's a little bit difficult to actually set up this kind of problem with SPH, but otherwise it's still agreeing reasonably well. And this is how the temperature looks. Now the temperature is a little bit different, and again the reason is mostly the hard photons and how deep you can get within the clump. And also the temperature behind the clump is somewhat different in some cases. But overall they do agree still. And this is the final state. So you have ionized most of the clump in this case. And you cannot evaporate it because obviously we don't have dynamics for this problem. But otherwise, yeah, the final structure is significant, quite similar, except for this one which is inner. And this one is because it has been doing actually a bit more, many more frequency beams, so it is different from the others how things are handled. And the temperature state, again, fair number of differences in this case. For example, how much you heat behind in the shadow, because on the limbs, of course, it's there is less column density, so you get some heating behind, and this varies somewhat. And also how much of this is shielded and so very cold. This could vary quite significantly between the codes, so there are some important differences here. How the ionization front evolves here. It's first very fast, propagates with something like over 1,000 kilometers per second, a few thousand kilometers per second. Then this is in terms of the speed of sound, twice the speed of sound. So when you reach 1, this is a D-type front, so it hits the clump, slows down, and then slowly gets trapped until it basically stops at the end. And this is the evolution in terms of radius. Again, fairly good agreement. This is a linear scale, so all the differences are quite small. The internal structure, as I said, again, main differences are how deep the hard photons are penetrating and how fast this happens. So some codes happens much faster than the others, so the remaining neutral fraction is lower in this case. But otherwise, the position of the ionization fronts agree quite well, and the structure is also quite similar. Now, some of the codes don't really have hardening here, so That's why they don't have more preheating beyond this point. So this is significant.
You're in discussion section now.
Yes.
Yeah. So 5 minutes to complete everything.
Yes, I'll do that. Okay, the cosmological case, again, fewer codes in this case, but there is, again, a fair bit of agreement. This is the ionization structure, the temperature structure. The cosmological field is actually not shown, but it is standard cosmological field with filaments and the halos in the knots of the filaments. The final structure, again, agreement mostly. So you have to keep in mind this particular one is not shown here because it didn't follow the temperature, but otherwise, yeah, there is good agreement between the rest of them, except that in temperature, this one is different because when you handle more frequency beams, then your final temperature actually depends on this, and it is a little lower in this case. Okay, so I'll skip this. So getting to the hydrodynamics, there is much fewer things to show, but in terms of the simplest problem, ionization propagation of ionization front in initially uniform density. In this case, of course, it's expanding, so you have the initial R-type phase where everybody agrees quite well. Then this is the analytical solution. Unfortunately, the analytical solution actually isn't quite a real solution in this case because it assumes, for example, constant density inside, and density isn't constant. But the numerical solutions agree between themselves much better than with the presumably exact analytical solution. So in this case, actually, there is no proper analytical solution. So what happens here is in the initial phase, the front is R-type, the density is constant. Then once it slows down, you start getting expansion from the inside, and a weak shock forms here. And then it propagates outward, sweeping the material outside, and you get much lower density in the middle, and you sweep a shock outward. So the speed of the shock, as you can see here, is a little bit different, and this mostly depends on the hardening in front of the shock. So if you heat the material a little bit, then the shock propagates actually faster than in cold one, and it's a weaker shock. Otherwise, it gets much stronger one. So that's why there is also some difference between the density jump here. None of them is actually really a strong shock. They are all weak shocks, but different level. The temperature structure, the same thing that we saw before. It starts in better agreement, and then as it goes, it actually starts disagreeing, and it moves with different speeds because of this preheating, which is different in different codes. The ionization structure initially in the R-type phase is all the same. This is the pressure. And you can see that basically they agree except for the hard photons again. But once you get to the D-type phase, the ionization structure is still roughly the same, except some are somewhat more diffusive. And you get, you see clearly the shock forms here in the pressure. You can see it, and start sweeping outward. And the position of the shock is somewhat different because of this different level of preheating in front. In the density, you can see it even more clearly because when it shocks, it rises the density, so you can see this dense shock sweeping outward. Okay, so I'm finishing. This is an interesting problem, which is basically the eye front is accelerating, then slowing down, and then re-accelerating again because it's a steep density profile, and it is quite difficult, in fact, problem. And you can see here that the results disagree, and we have to decide why and think about it more. And the final thing is, come on. The photoevaporation of a clump. So again, there is some differences which we need to discuss, but overall we actually agree fairly well on how fast it happens. how quickly, and the evolution is quite similar in different cases that we have here. So these are the summary.
Well, we already had quite a bit of discussion. I'll take one question and then we'll go on to the next.
As I mentioned, we will have at least 2 European radiation transfer benchmark projects.
Yes.
But they're dealing more with the dust. But from our experience from the SED benchmark, my feeling is it is quite clear that we will have one unique physical setup that all have to accept. And then, if you run the codes, you can see the numerical errors that are coming out and the weaknesses of the different algorithms that are used. Like you said, radiation transfer, Monte Carlo, they're very different. It's hard to nail down resolutions. And then we will have another run maybe where we differ the assumptions and can see what can be done beside. But I don't think with this approach where everybody can use different ionization rates, you will ever find out what are the numerics and what are the differences.
Well, it depends what you are shooting for, because after all, this is how people are using their codes. Otherwise, you're comparing codes that are fictitious because people are not using them the way you are comparing them. So
yeah, he's just saying there should be one intermediate layer to clarify what is what. Right?
Yes.
You're still agreeing that
but
this
that's
last
more
layer should be done.
necessary because they have relatively more complicated physics there, so they want to make sure their numerics is working properly. And we kept the physics relatively simple and trying to actually compare both the numerics and, well, the code as they are, essentially. So it's different approach. We can try also, I mean, we did the other thing as well, actually, just the opposite. We changed the rates to see the effect of the rates on the same code, which is sort of giving you some estimate what the effect of the rates is, apart from. But the main effect actually is not so much from the rates, but how you handle the energy equation and the spectrum. So the effect is some effect. The rates do give some effect, but it's a border at 10% or 20% at most. Any other difference are actually due to your method, not so much the rates.
Thanks. I think we have to move on. Perhaps there'll be more discussion of this later today. The next speaker is Masayuki Umura, who will speak about radiation hydrodynamic feedback and the formation of the first stars.
Good morning. So first I would like to thank the organizers to organize this such a nice meeting for the radiation hydrodynamics. And actually I started the radiation transfer calculation 13 years ago, so there are very few groups in the world. So now I'm very impressed by this workshop. And there are many activities in such a wide field of astrophysics. So what happened? Okay. So I'm talking about the radiation hydrodynamic feedback on the first star formation. But before that, I would like to show you some other 3D radiation transfer application for the cosmological application. That is actually the cosmic ionization. And also I would like to describe some 3D radiation hydrodynamics with SPH. And using such a radiation hydrodynamic SPH, so I would like to show you some application for the radiation hydrodynamic feedback on the first formation. And finally, I would like to introduce our recent project to construct a novel computer system dedicated for the astrophysical RHC. So this is the outline actually. And this is our previous simulation for the reionization of the universe. And this is actually the full 3D radiation transfer calculation with scattering of hydraulic photons. And maybe, okay. So this is the ionization structure is shown. So, and the color is actually the ionization fraction in this field. So we have assumed the isotropic ionizing radiation around this domain and computed the radiation transfer and solved the ionization structure finally. So actually we have done 100 times the iteration to converge the ionization structure. So this is our 3D simulation. And in this calculation we have assumed a very isotropic UV background around the computation domain. And then finally we have get what the ionization structure.
Do you have initially a lateral non-uniformity, or what caused the non-uniformity?
There is a non-uniformity in this domain, of course. But in this simulation, we have assumed that the isotropic radiation field, this radiation field is irradiated to the computational domain. So we have just assumed the isotropic background radiation in this case.
But the density is non-uniform.
Density is non-uniform in this domain, of course. Yes. And in this calculation, we have used the short characteristics method. So as everybody knows, so the short characteristics method is sometimes subject to the numerical diffusion. So, but if we consider the very diffuse photons, so this method is not so bad. But if we consider the very isolated source in the computation domain, so this is not so good. So we have improved this method to the more sophisticated scheme to solve the radiation transfer quite fast. And this is called ART. And the transfer is solved along the long range across the domain, actually. But the physical quantities are interpolated at each grid. And this coding is a little bit complex, but anyway, so one of the most best advantages is this does not have any numerical diffusion and accuracy equivalent to long characteristics. And the operation is similar to the short characteristics. And we have used such ART scheme to solve the ionization structure recently. So this is just a test for the beaming. So if you use the short characteristic scheme, so the beam is spread, and if you use this improved scheme, so the beam is just go straight. And actually, so we have applied for this code to the comparison project, and this is our art scheme. And anyway, so this is already described idea. And so in this scheme, so parallelization is a little bit tricky. So we have used the node wavefront method. So first, we should decompose the computational domain. So consider according to the number of CPU of the computer. And then solve the radiation transfer on this CPU, the computer. And then this boundary condition is transferred to the adjacent domain, adjacent region. And that's actually the different CPU in the computer. And simultaneously we can solve another direction of light with using this CPU. And so we continue this procedure. And so this is a kind of wavefront propagation in the computational domain. And finally, we can calculate the radiation transfer very effectively with the parallelization. And actually, the parallelization efficiency is more than 98%. And this is a very robust parallelization scheme. And actually, we have applied this scheme for the reorganization of universe for the point source case. So this is the POP3 case, and this is the black hole accretion case. So I don't say now the detail of this calculation because I have no time. But we can see the very detailed difference between such the source difference. So if you consider the POP3 stars, so the S region is more compact, and if you consider the black hole accretion is S region spread, and also the helium ionization is completely different from the two cases. Anyway, so now let me move on to the main issues of my talk. So that is relative feedback on the fast star formation. So according to the previous simulation on the formation of first stars, we know that the first object is order of the 10 to the 6 solar mass system. And also the POP3 star is 10 to the 2 or 10 to the 3 solar mass. That means a quite massive star formed at the very first epoch. And the question is how many stars formed actually in the POP3 object. And in that case, we should consider the relative feedback from the POP3 stars. And actually, there are three phases of relative feedback from dark age to the luminous age. The phase 1 is local feedback from POP3 stars. And that regulates the star formation efficiency and initial mass function in POP3 object. And phase 2 is the diffuse hydrogen molecule dissociation radiation background, which is built by the many stars. And such a dissociation photons can destroy the H molecule. That is the main coolant for the formation of POP3 object. And the phase 3 is the diffuse UV background radiation after ionization of the universe. So we should consider the galaxy formation under such a UV background radiation. So here I would like to show you some numerical simulation on the phase 1. So the problem is the feedback by the UV radiation from POP3 star is negative or positive. So there are several key physics. So one is hot heating. So the temperature is raised by the UV photon. And this can work negatively to form the POP3 stars. On the other hand, the ionization can promote the H molecule formation. So this can work positively to form the POP3 stars. And also there is a this is dissociation of H molecules. This is actually the Solomon process by Riemann-Bellner-Band. And finally, we should carefully consider the propagation of ionization front in this case. So anyway, so if first star forms here, and the star emits the UV radiation at the surrounding area, and maybe some star formation is controlled by such a UV radiation with the first stars. So we should carefully calculate such a feedback mechanism. So first, we would like to say about the formation of H molecule. And as you know, there is no electric dipole moment for the hydrogen molecule. So the direct combination to the hydrogen molecule is called mitten. So if we consider the very high density region, so three-body reaction does work. But anyway, after ionization or at the epoch of the formation of the first stars, so the density is not so high at the initial epoch. For example, the 10 to the 100 cubic centimeter per cubic centimeter at the recombination epoch. So in that case, there the reaction should be required to form the hydrogen molecule. So one famous reaction is the electron reaction. The other is the proton reaction. So the hydrogen combines with the electron and forms the H minus, and this H minus and H can react to form the hydrogen molecule. And this is proton reaction. Anyway, so in other words, these reactions need ionization of the media. So if there is no electron at the initial epoch, so no hydrogen molecule form. That's one point. And also, UV radiation can dissociate the hydrogen molecule by Solomon process. So actually, the hydrogen molecule cannot be disrupted by directly the UV radiation. So first, the UV radiation excites the hydrogen molecule to the excited state, and that excited state decays to the continuum level. So actually, the 15% of excited state can decay to the continuum. So this is equivalent to the photodissociation. This is a little bit tricky physical mechanism. And 80% is populated by rotational level of the hydrogen molecule. This is called the Solomon process. So we should consider such a process to form the hydrogen molecule to the oxide formation. And the final one is the ionization front. So this is a very classical theory for the ionization front. If we consider photon conservation, so we have basically two solutions. So one solution is the R type. This is the first ionization front propagation. And the other is the D type. This is slow propagation, ionization front propagation. But this is some there is some range for the R type for the velocity of the ionization front, and also some range for the D type ionization front. And between this velocity and this velocity, VR and VD, there is no direct solution for the ionization front, but there is the intermediate solution between the VD and VR. So this is actually accompanied by shock. So in this case, the ionization front, ahead of ionization front, shock is arise. And actually this area is B type, and this is so the problem is we should couple this ionization front with the gravitational instability. So if the UV radiation irradiates the adjacent collapsing cloud, which is a runaway cloud under collapsing. And so in that case, this region is similar to the scale of Jeans wavelength. So you can easily find, in this case, if you consider the R-type ionization front, the front propagation time scale is always smaller than the free fall time for the R-type ionization front. In other words, R-type ionization front propagates always before the gravitational cloud. So in this case, this cloud can evaporate by the hot heating. And on the other hand, if you consider the B-type ionization front, so the propagation time scale is always longer than the free fall time. That means the gravitational collapse occurs before the D-type ionization front propagates. In this case, the gravitational instability cannot be prevented by the ionization. This is a very simple argument, but we don't know the answer. We don't have an answer for the N-type ionization front, so which is accompanied by shock. So we should solve such a mechanism carefully. So actually, we have used RSPH scheme to solve this problem. And this is the hydrodynamics is based on SPH, And the cell gravity is solved by the parallel 3-grade scheme. And this is a frequency-independent radiative transfer. This is actually the ray tracing. And also we have included the non-equilibrium chemistry and some process for the formation of hydrogen molecules. This is the kind of concept to solve the radiative transfer based on SPH. So we just calculate the optical depth from the target to source. So first we should find the nearest SPH particles along the line of sight. And then the physical quantities are projected onto this line of sight. And then they calculate the density or the hydrogen degree or something like that. So, and then we can estimate the optical depth along the line of sight. This is our basic concept. And also we have done the parallelization of radiative transfer with using this scheme. This is basically the orthogonal recursive bisection. So there are many SPH particles, and if there is a source here, so we should solve all of the line of sight for the SPH particles. And if we would like to solve for these particles, so this line of sight intersect the many domains. So this is belong to the different CPU in the system. So,
please?
Yes.
The size of an SPH particle that you would use in the hydro need not necessarily be the same as the size that you use for the radiative transfer. So what choice do you make?
Yes, but in this case, actually, the same the SPH size is done by the hydrodynamics.
Yes.
Yeah, not the radiation transfer.
And you use the same.
Yeah. Yes. Exactly.
Thank you.
Yeah. And if there are many sources here, so we can use again a sort of node wavefront method for the parallelization. So this is also based on the orthogonal recursive bisection. Okay. It's a little bit complicated, so I can not say detail now, but yeah. So this is the test program which is already shown Ilian, and this is our SPH scheme. This is the distribution of temperature, I guess. Yes. And this is our SPH scheme. This is RH1D calculation. I think this is a forward group. Okay. Yeah. So compared to the 1D calculation, so this is looks good. So, and we have used this scheme actually, and we have set a very simple model. So there is a collapsing cloud and also the toxic star. And in this calculation, we have assumed the number of particles is 500,000 particles, and the source star is 120 solar mass. And we have changed the size of cloud and the distance of source, and we have checked the final result. So this is one typical result for the H2 shielded flux. This is a sort of high density case. So in this case, this shows the temperature of the hydrogen front. So this is the ionized region, and this is neutral region. And at the boundary, you can see the hydrogen front, and also there is a shock front here. So this shock front is actually the N-type hydrogen front. And in this case, the shock front finally evolved into the D-type. And then the collapsing cloud cannot prevented by the UV radiation from the star. So it's in other words, the collapse succeeded in this case.
So this is hydro.
This is full 3D radical
how many
hydro.
turnover times? I mean, how many sound travel times would that be? This is the duration of the run on the right.
You mean the physical time?
The sound travel time.
Oh,
Sound domain size divided by the speed of sound.
yes, yes.
How much?
Time scale is 10 to the 6 years.
And the duration of the run was what?
10 to the 7 years.
Yeah, thank you.
Yes.
Thanks.
And actually, the important point is in this case, the ahead of the ionization region, ionization front, the hydrogen molecule shell formed by the weak ionization by the UV radiation. So this hydrogen molecule shell can seize effectively the Riemann-Bellman band radiation. In other words, so Riemann-Bellman band radiation cannot dissociate the hydrogen molecule in the collapsing core. So that can help the collapse of the core. So this is a very important mechanism in this case. And the other case is the relatively low density case, and this is shock-driven evaporation for the cloud. So actually, if the density is relatively low, so the shock propagate and the hydrogen front become N-type, and the shock can evaporate the core gradually. And finally, this cloud cannot collapse. Okay, so this is the low density case. And we have changed the distance of stars and the density of clouds, and we have obtained the final result for the collapse of the cloud. So this dark means the collapse succeeded, and this cross means the cloud evaporated. And you can see the very narrow region is prohibited for the collapse in this case. So if you consider the POP3 star formation region, so these areas correspond to the POP3 star formation region. So in other words, almost all regions, the secondary star formation can occur, even for the first star is shining. So, and with using final several minutes, so I would like to show the new attempt to construct the computer. So this calculation is not so many particles. So, and we would like to expand this calculation to the very large radiation hydrogen simulation. So in that case, we need the very fast computer. For example, the host performance is several teraflops, and the gravity calculation is several 10 teraflops. So we need such a heterogeneous new type of computer. And actually, we are now preparing the project that's called FAST. The FAST means the fusional integrator for the radiation hydrodynamic system in Tsukuba University, my university. And this is for the elucidating the original first generation objects. The first means two kind of meaning actually. So and anyway, so we have started this project 3 years ago and almost completed. So we have used around $3.6 million US to construct this computer, and this is a collaboration between the astrophysics and computational scientists. And we have newly developed the special purpose computer for gravity calculation. That is called Gray X64. So the one important point, this board can be embedded to the each node in the PC cluster with using a PCI bus. So the performance is 136 gigaflops for each board. And finally, we have constructed 256 node system with using such Gray. And the total performance is 36.1 teraflops. And that is, includes the host is 3.1 teraflops and Gray 33 teraflops. And it has a total memory of 1.6 terabyte. And the total storage is 22 terabytes. So now we are using this new type of computer to solve the radiation hydrodynamics, especially to explore the formation of fast stars. And this is just ongoing calculation. Now my collaborators are calculating. So this is basically the PQM Gray space simulation. And on the formation of feedback of fast stars. This is the actual lambda CDM cosmology achieved. And we have used 200 million dark matter particle and SPH particles. And the mass resolution is 0.3 solar mass, and the total mass is 6 times 10 to the 7 solar mass. And we are now calculating the evolution of the fast structure in the universe. Unfortunately, I cannot show you the detail at now. So this is just ongoing project. So it takes several months to have the final result. So I would like to show you the final result later. So let me summarize my talk. First, the economical related transfer code that is called ART has been developed. This code does not have any numerical diffusion, and SPH is fully coupled with radiation transfer and non-equilibrium chemistry using RST. To explore the related feedback on fast star formation, it is necessary to resolve M-type ionization photon accompanied by a shock. And so we have a result on this feedback. So the secondary star formation is possible in the broad region of populous star objects. And finally, the first simulator has been built up for the Grand Challenge for the large RHD simulation. And now intensive simulations is started with this new type of computers. Thank you very much.
Thank you. Discussion. Paul?
Just with regard to the fourth bullet on the secondary star formation.
Yes.
I'm going to talk again about that this afternoon. But a simple description of what we were finding is that in the presence of the radiative feedback of the first star, the secondary formation has a rather neutral feedback effect. That is to say, if the mini halos were destined to form stars before they were hit by the ionization front and dissociating radiation of the neighboring star, then they continue to be able to form stars. If they were not going to be able to form stars, the radiative feedback doesn't induce star formation. So to details aside, it's a largely neutral feedback.
Yeah.
It can speed up the process, it can slow it down, but it won't change the outcome.
Of course, it depends on the size of the system. So if you consider the mini halo or the small galaxies, so
we're talking about mini halo.
Yeah, mini halo. Yes. Yeah, so in that case, the gravitational field is different from this case. And the mini-halo can collapse by the UVAC and the compression. And this is another story, actually.
Yes, well, you were parameterizing things
right.
According to the density.
Yes.
So including structures within a mini-halo, for example.
Yes.
But I was talking about mini-halo itself.
Okay.
So the advantage with doing these, what we call long characteristics, but there's a confusion about what's short and long and what's, we call it authentic radiator transport, is that it doesn't have any diffusion, but on the other hand, you need to have many directions to cover the radiation to not miss anything. Is this a case with only point source functions, or do you have diffuse radiation as well?
Of course, we can consider diffuse radiation as well. So, but if you take the diffuse radiation, the computational cost is very high, and of course, yes, sorry. Yes, so the direct long characteristic method, you should solve the each line of sight from the grid point to the grid point. But in this case, we just solve the parallel line of sight from the boundary. And in some cases, there are many sources in this area. And also, in some cases, we should consider the scattering photon in each grid. But it doesn't matter. So if you take the parallel line of sight from the boundary, so you can just solve the radiation transfer according to this ray. And what difference between this method and the direct long characteristic method is just the number of ray. Number of ray actually between the grid and grid. And this is just one difference. Yes.
So how many rays do you have?
In this case, this n theta is equivalent to the nx or something. So the same resolution of spatial resolution.
Area.
In your simulations, do you take into account the radiation force?
Yes, no, not yet. It's not important in some case because the first star is very massive. Then the radiation force can work in some sense to form the. I mean, the first star is nearly Eddington luminosity, right? So in that case, in the very adjacent region, the radiation force can work to prevent such a mechanism. But at present, I've not included such a. So in the future, we will.
Did anybody's calculations cosmological?
I don't know.
Axel.
We have, and I can talk to you about it afterwards.
I think.
Wait a second, Paul. Axel's next.
Some of the reactions involved photons. So does it actually mean that your chemistry includes also the intensity field, or the mean intensity probably rather?
Right. Yes.
Okay, we would like to see that maybe at some point.
Yes, yeah. All the chemistry is included.
Yeah.
Too, so.
I have an elementary question, since I'm not familiar with these cosmological simulations. What is the actual bottleneck, or which process forms the actual bottleneck for your calculations? You have hydrodynamics, radiative transfer, gravitation, self-gravity, and chemistry. And you have accelerated the gravitational forces by special, or the calculation of the gravitational forces by special hardware.
Yeah, actually, in that calculation, the most computational cost is solving the non-equilibrium chemistry coupled with the radiative transfer. That is the most time-consuming part. Yeah, and the zero gravity is not so heavy in this case. So, yeah, in other words, post computers should be much more faster. Okay.
Paul.
I think it would have been useful for the audience of non-cosmologists to lay out what the basic problem regime is a little better than we have so far this morning. First of all, We are in a regime in which the momentum equation term due to the radiation field is negligible. We don't therefore add it into the momentum equation. We don't add it as a term in the energy equation. We only worry about the intensity, the mean intensity, at each point in space. And we unfortunately have to consider a range of scales. And this means that ionization fronts can travel from the speed of light all the way down to highly subsonic speeds of less than a kilometer per second. And sometimes the gravitational clustering problem is only relevant to produce the locations of galactic halos that are sources on large scales. And sometimes it's necessary to follow the collapse of a mini halo to form a star.
Right.
So all of those scales are happening at once. So you have to pick your problem and your scale. And that's why there's not a simple answer to that. Right.
Maybe difference from the solar physics and this cosmological application is just the cell gravity is included for such problem. So the cell gravity is coupled with ionization front and shock, and such a marked difference. Yeah.
Okay, we're going to break for coffee now. We'll reconvene at 10:50. Let's thank both speakers.